Hi everyone, welcome to our second video in our Kinetics series. So if you haven't watched episode 10, please stop. You're doing this out of order. Go back to episode 10 and then come back to us at episode 11 here. So episode 10, the last one, that was on reaction rates. That is your macroscopic perspective. And so now what we're going to do is try to look at our rate laws, or more importantly, derive our rate laws, which is going to give us the microscopic point of view. So this is a slide from the previous episode, so you've already seen this. We had our example equation where we had methyl chloride and we reacted it with our hydroxide ion. We were able to produce both methanol and then the chloride ion. We primarily looked at the macroscopic side of this in the last episode. So we looked at our rate of reaction and how quickly the reactants are used up and then how quickly the products are formed. So how quickly can we use up that hydroxide ion and then actually form that methanol product? So this is the macroscopic point. We measure this in lab. This is something you can do with a stopwatch. I'm being a little goofy with that. Obviously, you would use more technical instruments and whatnot, but you can measure this in lab. Now, what we're going to do in this episode is take it one step further. So just look at the bottom part of the slide down here. And so the rate of this reaction actually depends on the concentrations of two reactants. In this example, two reactants, because we have two. So then this expression is known as the rate law. And that's the whole point of what we're doing today, is figuring out what these rate laws are. So in the last episode, we talked about how concentration, or more importantly, collisions, actually dictates how fast a reaction will proceed. Now what we're going to do is use data and derive a rate law so we can start to make predictions. Remember, as chemists, we don't really care about our evidence and our data. What we care about is how we can use that, manipulate it, come up with a reaction or an equation, more importantly, so that we can predict future reactions. It's all about predicting reactivity, and that's what a rate law allows us to do. So, oh, and my computer's frozen. Come on, there we go. All right, so the first thing we're going to do is look at an example. And so this is an empirical rate law for a generic reaction, which is A plus B, which gives us C plus D. So this is our rate law, where rate is equal to K times the concentration of A raised to the X power times the concentration of B raised to the Y power. So I'm going to point out a bunch of different things here for you. First thing is that this is going to be our rate. So our rate has a very specific unit. It's always going to be in, let's write out units. The units are always going to be in concentration, so molarity usually, and you're going to divide it by some kind of time component. There's always a time component, because remember, it's kinetics. So usually we do things in seconds, but sometimes it's minutes, sometimes it's hours, sometimes it's days. There's just some type of component for time. A and B, you'll notice, are concentrations, so those are going to be in a concentration of molarity, so capital M. X and Y are called orders. Okay, X and Y are called orders. What is that, right? We're going to talk about that in just a second. And then obviously I see that there's K here. I just want to tell you that's a rate constant. I'm going to come back to that in about 2 slides, but just know that I'm coming back to that, okay? So X and Y are called orders. And what the heck are orders, right? So in kinetics, we have these things called reaction orders. And so some reaction rates depend heavily on the concentrations of the reactants. Some don't, okay, but most of them do. And so the reaction order is the degree to which the reaction rate depends on the concentrations. So what we can do is look at the order of each species. So that is going to come from your exponent. It's your exponent for each species. Okay, so in our last example, wow, this pen is terrible. So in our last example, we had rate, which is equal to K times A. And let's just say it's squared, and then we'll multiply it times the concentration of B. Okay? Apologize for the pen, guys. It's the lag of the recording. I promise I'm not drawing that squiggly, but whatever. So if we were going to look at the order of each species, that comes from the exponent. And so A, in this example, would be second order. We can tell that because of the 2 raised there is the superscript, or your exponent. So A is second order. That means our reaction rate is going to heavily depend on the concentration of A. And the more A we have, the faster it's going to be. It also depends on the concentration of B, but because there's an implied 1 right here, we would say it's first order. So the reaction rate depends on the concentration of B, and it really depends on the concentration of A. So as a scientist, right away, I'm more focused on A. Your overall reaction order, though, that's just the sum of your exponents, or the sum of the order of your other species. So this, in this example, would be X plus Y for the last slide, but here would be 2 plus 1, which is going to give us an overall reaction order of 3. So if I asked you, what is the order for A, you would say 2. The order for B, you'd say 1. And the order for overall for your reaction is 3. So that means it really heavily depends on the concentration of your species, or how many particles are involved in the reaction. Now, I told you I'd come back to K, so here we go. Now, here's your rate law, just a generic rate law, where your rate is equal to K times the concentration of A to the X power, concentration of B to the Y power. Haven't changed anything here. Rate, we said, has to be in concentration per unit time. I'm just going to write seconds here just to make our lives easier, but molar per second. Now, if for this example, we do have a 1 right here and a 1 right here, that means we are going to have K, rate constant, times the concentration, molarity, times again, concentration for B. So in this one instance, our unit for K is going to have to be 1 over molar times second. Okay, has to be. There's no other way around that, because our m's are going to cancel out, and that's what's going to give us an overall rate constant itself. Rate of the whole reaction is molar per second. The rate constant, however, is going to have a unit of 1 over molar times second. Now, if we have something that was a different rate law, like rate is equal to K times just A by itself, okay, just like that, our rate is going to be molar per second. That hasn't changed. Our rate constant, those units are always changing. And then our concentration of A, that has to be molarity, big capital M. Well, in order for us to do something times molarity and get molar per second, in this example, the rate constant would just be 1 over second, or inverse second. Okay, so your units of K are always changing, and in a couple slides here and in the next episodes, we're going to start to see how the units of K can actually clue us into determining if we have something that's 0, first, or second order, and we'll go over that in just a second. But before we do that, I want to give you a chance to look into order, make sure you understand what that is, and so we have a mini activity. All right, so your rate law for the following reaction rate is this. Its rate is equal to K times your concentration of carbon monoxide times your concentration of water. So what I want you to do is stop the video, pause the video, and answer 3 questions. First one, what is the order with respect to each reactant? What is the overall order of the reaction? And what are the units for this specific rate constant? Okay, pause the video, try it. We were lucky with this problem because they already gave us that rate law. And so that's rate is equal to K times the concentration of carbon monoxide times the concentration of H2O. So unfortunately, these rate laws are something that you either have to derive from data or hopefully are given to you. You cannot just look at the coefficients in your reaction and be like, oh, it's just an order of 1 or an order of 1. In this particular example, that is actually what it is, but you have to use data to back that up in order to derive your rate law. Have to. All right, so the first question here is, what is the order with respect to each reactant? So we'll go here and do these one by one. What is the order with respect to each reactant? So for carbon monoxide, what we see is there's an implied 1 right there. So we would say it's first order with respect to carbon monoxide. And then for water, again, there's an implied 1. And so again, we would say that this is also first order. So each of these are first order for carbon monoxide and water. Notice we're only doing this for reactants, okay? All right, so for number 2, actually, let me go back to that. Why is that? Okay, why are we only doing this for reactants? The reason we are only doing this for reactants is because we're trying to predict how long this reaction is going to take, and that depends on the concentrations of your reactants. At time 0, you don't have any products, and so, well, in theory, right? So you don't have any products, and so you have to be only monitoring the concentrations of your reactants. Now, further down the line, we'll get to a point where that's not 100% true, but for right now, we're just going to focus on those reactants. All right, so now number 2. What is the overall order of the reaction? This is the easy one. You add the 2 numbers together. It was first order with respect to carbon monoxide, first order with respect to water. 1 plus 1 gives us 2. Easy question, okay? Number 3, what are the units for the rate constant? Okay, so this one we actually have to do a little bit of thinking. So we see that it is first order with carbon monoxide, so we can just put 1 molar right there. First order with respect to water. We're going to multiply that times the rate constant, and that's going to be equal to our rate, right there, okay? So that is going to be molar over, and let's just say seconds, okay? We'll just dictate what the time frame is. So in order to get molar divided by seconds, and if our rate constant is what we're looking at, we know that we have to do molar times molar, and then our rate constant has to be 1 over molar per second in order for us to get an overall rate constant of molar per second. Because then our molarities cancel out, and you're left with molar divided by second, which gives us the rate constant, so that works. So just to be super clear, our unit for this rate constant is going to be 1 over... give me my pen back. 1 over molar times second. Okay, so that's going to be your unit for K. Again, this always changes. You can't assume that's true for every rate constant. Okay, so now we get to one of my favorite parts of kinetics. I absolutely love doing this, so yay. All right, so in our last episode, what we did is we assumed that this reaction required a collision between our methyl chloride and our hydroxide ion. We had to assume that. A reacted with B. As soon as they hit, that's what allowed for the chemical reaction to begin. But now what we're assuming is that our rate would be directly proportional to the concentrations of each reactant. We wrote the rate law for the reaction as this, so we gave that to you. Rate is equal to K times your concentration of methyl chloride times your concentration of hydroxide. So what we're going to do right now is actually use real data and see if that rate law was accurate. We just gave that to you for the first episode because we didn't want to make anything confusing, but now let's back up and see if that's accurate. So what I've got here is a mini activity for you. We have 4 different experiments. If you watched the last episode, you would recognize these 4 snapshots as our different solutions that we had, 1, 2, 3, and 4. And now what we're going to do is pair them up with specific concentrations. So you will see that the ratios we determined in the last episode have stayed true here. So we actually have a 1-to-1 or 1-to-3 ratio and whatnot. And then what you will see is we actually measured their initial rate. So at time 0, where the rate is fastest, we've measured how quickly we were able to convert our reactants to our products. So what we're going to do here is use this data to see if we can derive the overall rate law for this reaction. But we have to use this data. This is the only information we have. And I want to put it out there that there's like a million different ways of doing this. I have a very specific way of doing it, and it's my favorite way, and I think it's the best way. But if you talk to my TA Amanda, she has a completely different way. If you talk to other TAs, they have different ways. So this is really just something kind of like Lewis structures where you need to make up your own method and just stick to it. And as long as you end up with the right answer and you follow the correct protocol, then you're totally fine. So just make sure you're doing something that seems logical. All right, so the way I do this is I start off by looking at 2 lines that are similar, but there's one change in the concentration. So right away, my eyes are drawn to line 1 and line 2. So what I see here is that my concentration for my methyl chloride has remained constant here. It's 0.1 molar and 0.1 molar. But then my concentration of my hydroxide ion has actually tripled. Okay, so we've multiplied it by 3 to go to 0.1 to 0.3. So what we're going to do here is come down here to see if we can start kind of deriving this. And just stick with me. In the beginning, my method feels a little funky, but after like 1 or 2 examples, it all clicks. So the first thing we have to do, step 1, is we're going to write out our rate equation. So our rate law. So we have rate is going to be equal to K times the concentration of CH3Cl. And we're going to raise that to the x power, the order of x. We don't know what it is yet. And we're going to multiply that times our hydroxide concentration. That's going to be raised to y. Again, we don't know what that order is yet. That's what we're trying to figure out. Okay, so like I said, we're going to look at lines 1 and lines 2. So lines 1 versus line 2. So the first line, no matter what, you're always going to use the number 1. So you've got K times 1 raised to x, 1 raised to y is equal to 1. It's always 1, no matter what. Okay? Now what we're going to do is we're going to compare lines 1 and line 2 here. We're going to look at the 2 lines, and we're going to see the differences between the 2. So we're going to actually take line 2 and divide it by line 1. So 0.1 divided by 0.1 is 1. So we're going to come down here. We're going to have K is equal to 1 raised to x. So the second line is line 2 divided by line 1. Okay? So now we're going to go over here for our hydroxide. 0.3 divided by 0.1 is a difference of 3. So 3 raised to y. Now we're going to come down here and look at our rates. What we see for our rates is that our first line had a rate of 5 times 10 to the negative 6th, and then our second line has a rate of 1.5 times 10 to the negative 5. So I'm going to take this number and I'm going to divide it by this number. And when I do that, I get a number equal to 3. So now I have two mathematical equations, and I am able to then isolate what y is equal to in order for both of my equations to be accurate. So 1 raised to the y power is equal to 1, 3 raised to the y power equal to 3. The only number y can be equal to is 1. Has to be. So we just figured out what the order is of y. Yay. Wonderful. Now what we need to do is figure out what the order is of x, or what x is equal to. So we're going to come back over here, and now we're going to look at something where the concentration of our methyl chloride changes, but hopefully our concentration of our hydroxide remains constant. So I'm going to come back through and remove these lines to make it simple for us again. And now what we're going to do is focus on lines 1 and lines 3. Okay, lines 1 and lines 3. So here what we see is our concentration for our methyl chloride goes from 0.1 to 0.3. We multiplied it by 3 again. But our concentration of hydroxide remains constant, 0.1 to 0.1. Again, what we see is that our rate increases by a factor of 3 as well. So we're going to come down here, and I'm going to write all this out in my goofy, awful handwriting because of this software, because I'm going online, but whatever. Okay, line 1 versus line 3. We're going to use the same rate laws that we had before. So now we're going to put in our rate constant k, 1 raised to x, 1 raised to y. We know y is 1, so we don't have to put y in there. And we're going to say it's equal to 1. Perfect, easy. Second line, k is going to be equal to something times x, something raised to 1 equal to something else. And this is going to be line 3 divided by line 1. Okay, and that's supposed to say line 3. Let's try that again. Line 3. Not much better, but we'll take it. Okay, so we're coming up here. Line 3 divided by line 1. So for our methyl chloride, this was a 3. 0.1 divided by 0.1 is 1. 1.5 times 10 to the negative 5 divided by 5 times 10 to the negative 6 is 3. So we end up having 3, 1, and 3. It's the exact same math as above, except for we've just swapped the values for our methyl chloride and our hydroxide. So again, the only way mathematically for this to be accurate is if our value of x is actually equal to 1. So again, we've just figured out what our order of x and y is, which is fantastic news. So now what I need to do is put this all together to see if I can determine my overall rate constant. Like, what is k equal to? So rate is going to be equal to k, that's what we're now looking into, times our concentration of our methyl chloride, raised to 1, times our concentration of our hydroxide ion, again raised to 1. But I don't actually like seeing that because that's just it's unconventional. Alright, so now what we're going to do, since we know our orders with respect to both of our reactants, we're going to go back up to our data, all the way back up here, and you can pick any one of these experiments to plug it into your equation to solve for k. When I was in undergrad, I actually messed up these lines and I missed a question on my Gen Chem exam, and so from here on out, I have always used the line or the data from experiment 1. You will never see me use a different line because my eyes jumped once when I was 18 and I still haven't forgiven myself for it. So I'm going to come all the way down here and plug these numbers into our equation. So if we do this correctly, we're going to see that our rate, again, I'm just pulling it from from the table, our rate was equal to 5 times 10 to the negative 6. That was molar per minute. We're going to set that equal to k. We're going to multiply that times the concentration of that methyl chloride, which was 0.1. We're going to multiply that times the concentration of our hydroxide, which was also 0.1. And if we do that properly, we can solve for k, and we get a rate constant that is equal to 5 times 10 to the negative 4. Now, to check our units, the only unit that can make this accurate, this entire mathematical expression accurate, is that if our rate constant has a unit of 1 over molar, and this time it's times minute, okay, so minute. 5 times 10 to the negative 4th, units of inverse molar times minute. It's a very weird unit, but that's the correct one. Okay, very last step in the whole thing is you have to put this all together to give us our overall rate law. This is the whole point of it. So if we did this properly, we would end up with a rate law where our rate is equal to that rate constant, 5 times 10 to the negative 4, 1 over molar times minute. It's going to be equal to our concentration of CH3Cl times our concentration of OH minus. And that, my friends, is our beautiful, gorgeous rate law. I would encourage you to stop right here, pause the video, go back all the way through to the top. Just pause the video on this spot right here where you can see the raw data. Go through, see if you can derive that rate law for me right now, okay? Hopefully you do. You're probably not going to, but hopefully you do. And after you've done that, what I want you to do is go through and do this mini activity. So I want you to try one on your own. So here, I've now given you a new equation. So now we have A plus 2B going to C. I've given you some data. It's simple here. I've given you 3 experiments. What I want you to do is use this data to answer 4 questions. Number 1, what is the order with respect to A? So in our example so far, that would be X. We're solving for X. With respect to B, that's the order with respect to B. That's going to be our coefficient, or excuse me, our exponent Y. And then what is the rate constant? So that's our K term. What is the rate constant? And then what are the units of the rate constant? I actually want you to take this one step further and give me the overall rate law. So answer the 4 questions to give me the rate law. Stop the video. Do this. Please do this. Please. All right, let's work through this one together. So I'm going to just scroll ahead here so I have a little bit of space. The first thing I'm going to do is come up to the top and cross this out. The chemical equation gives us 0 information here. Just cross it right out. It doesn't even help us. The only thing that is useful is this table of data. That's the only way we can find our rate law. All right, so the first thing we are asked is to solve for the order with respect to A. So what I'm going to do is come up here to my table and kind of analyze how my concentrations change. And right away, what I see is that I don't want to solve for my order of A first. I actually want to solve for my order of B first. And the reason why is because I can look at line 1 and line 3. What I see here is that my concentration of A is held the same or held constant in my experiment 1 and experiment 2. But my concentration of B was actually doubled, so times 2, when we went from trial 1 to trial 3, or experiment 1 to experiment 3. And so this is super important to me because I can see really easy math, just doubling something is easy, so I'm going to start with that one. But again, you can pick whatever you want to solve this, just figure out a method that works for you. All right, so I'm going to start off by comparing lines 1 versus line 3. And we're going to do this by starting off with a generic rate law. So rate is equal to K times our concentration of A raised to X times our concentration of B raised to Y. Now, like I said before, you're always going to start off with 1s in your first spot. 1X, 1Y, equal to 1. Now we're going to come through and we're going to divide line 3 divided by line 1. Okay, so when we do that, K stays the same. Our A value, we have 0.1 divided by 0.1, that's 1. Then we can come here, 0.2 divided by 0.1, that's 2. And then we have 2.74 divided by 2.73. That's essentially the same number, at least in kinetics, and so we're going to put that as a 1. So mathematically, the only way for this to be true, where 1 times 1 is equal to 1 and 1 times 2 is equal to 1, is if our order with respect to B, oops, I almost got really excited about that, our order with respect to B, Y, is going to be equal to 0. That is the only way mathematically for 1 times 2 to be equal to 1, is that the Y has to have an exponent of 0, or order of 0, okay? All right, so now we're going to do this again, and we're going to try to solve for X. So this time, we're going to go back up here and see what other trials we have. This one is much easier. We only have another one to compare it to. So I'm going to get rid of this right here so we don't get confused. Now what I'm going to do is compare experiment 1 with experiment 2. And so what we see here is this time I actually see that my concentration of B remains the same. Nothing changes there. We have an order of 0, so it doesn't really matter. At this point, you could put a line through this because it doesn't matter. The concentration of B does not affect the rate. That's what we just learned. So then what we need to do is figure out how the concentration of A affects the rate. And so we're going to see that as we go from experiment 1 to experiment 2, we actually multiplied by a factor of 1.5, which is kind of unique. Most of the time we double it or triple it, but whatever. And then what we see here then is that our rate actually increased by a factor of 2.25, which again, a unique number, but if you're a math person, you probably see where this is going. Okay, so we're going to come down here. Plugging those values in. This time we're comparing lines 1 versus line 2. So we have rates, is equal to k, which is not going to change, and that's going to be multiplied times our 1 times x. Again, since we saw that our order for b is 0, we don't have to include it anymore. It's gone. Doesn't affect the rate. Get rid of it. Only messes with our math. And we're going to set that equal to 1. Now again, for our second part, we're going to set line 2 divided by line 1, and that's how we're going to come up with these numbers. So now here we have k times, we're going to go back up here. What we saw is that we increased this by a factor of 1.5, increase our concentration, that is. So 1.5 raised to x, and then we saw that our rate actually increased by a factor of 2.25. So we're going to come down here and write 2.25. So mathematically, the only way for this to be true is if x is equal to the value of 2. So 1.5 squared is equal to 2.25. No, I don't expect you to actually know that, but I do expect you to have a calculator, and if you put 1.5 squared in there, you're going to get 2.25, so I believe you can know that. But now you know it, okay? All right, so next part is we have to figure out what our rate constant is. So we're going to write rate is equal to k times our concentration of A squared. We just learned that the order is 2. We're not even going to put B in there. B does not affect the rate. So now what we have to do is plug in our values so that we can solve for our rate constant, which is K. Let's come all the way up here. Again, like I told you before, I don't like looking at any other line except for experiment 1, so that's what I'm going to do here. So I'm going to look at the data in this line, but again, we don't care about anything that's written in column B or in the concentration, this column right there, because B doesn't affect the rate law. So we've got 0.1 and then 2.73. 0.1 and 2.73. So 2.73 is our rate. The unit of that was molar per second. We're going to set that equal to our rate constant K. Then we're going to multiply it by that concentration, which we said was 0.1, 0.1 molar. We're going to square that value. If you put this into your calculator properly, you're going to solve for your rate constant to be 273. And then the proper unit for this is going to be inverse over molar times second. Okay, you should be able to prove that to yourself. Molar squared, there's going to be 2 molars here. You're going to have to cancel a molar component out so that you're going to be left with molar over second for your overall rate law. Hopefully you got that right. If not, stop the video right now, go back, figure out where you made your mistakes, take advantage of the fact that this is an online course now and you can slow me down, you can stop me when I go too fast for you. So go back, rework the problem, and figure this out. Okay, you have to be in charge of your own learning now. All right, so that is actually the end of this episode, and so what we're going to do next, let me just give you a hint, is we're going to go to integrated rate laws. So we started with reaction rates that bred us into rate laws where we can use our data that we have in lab to figure out what our overall rate laws are. Now we're going to take it one step further and be able to use a current concentration to predict a future concentration, or maybe a time component, or maybe a rate constant. This part's awesome, okay?